All right, gang. More on confidence intervals for proportions. Again, confidence intervals for means will be taught in a later video. Right now, our focus is on confidence intervals for proportions. I think the confidence intervals for proportions is a little harder because the standard error is a little messier. But hey, we'll survive, right? Uh, Next on the schedule is to be able to determine sample sizes given, or at least in the context of a confidence interval for proportions. So first of all, maybe we're just given a confidence interval and we need to determine what sample size was used to calculate it. Well, there's a strategy for that, and I'm going to teach it to you. The next thing we may have is we may have a particular confidence interval where we know the sample size, but we need to know what sample size would be needed to reduce a margin of error. For example, let's say we're trying to estimate something and our margin of error is really high, maybe 10%, plus or minus 10%. Maybe we want to reduce that to 3%. You know, what sample size would be needed to accomplish that? And of course, the third thing we may need to do is determine what sample size would be needed if no estimate, in other words, p hat, was not available to estimate the p that we're trying to get some information about. All right, so let's just review a little bit or revisit. We know that the confidence, and I will warn you, this is going to get a little messy in terms of the algebra, but just stick with me. Once we get to the final, okay, this will be something that you won't have to replicate. You'll just have to use the information that I create. All right, so we know that the margin of error, sometimes M, sometimes E, just depending on the context, can be found by the critical value. And again, this is alpha over 2, but I'm not going to write the alpha over 2 because it just makes it messy, times the standard error, p hat times 1 minus p hat over n. Now, what I'm trying to do here, again, the focus is on finding a sample size that meets certain conditions. So I want to isolate that n. In other words, I want to do algebraic manipulation where I just have n equal, a bunch of stuff. So the very first thing I would do is I would divide both sides by my z critical. So again, on the left, and again, it's just known this is z alpha over 2, okay? That's just ugly. Let me see if I can... Let me freeze that. All right. And then on the right, we have the square root of p hat times 1 minus p hat over n. Why, it took me literally. It just literally froze it, okay? Again, just divide. So what I would want to do next is I'd want to square both sides for obvious reasons. I want to get rid of that square root sign. This is really annoying. So on the left side, I have the margin of error over the z critical squared. And on the right side, I have p hat times 1 minus p hat over n. Now, keep in mind that a lot of textbooks will define this 1 minus p hat as q. So I'm just going to start using the q. Well, in this case, it would be q hat. Q hat, just to make things a little bit cleaner. So I have the margin of error over z squared equals p hat times q hat over n. Just makes it a little cleaner, saying the same stuff. Now, the next thing I need to do is I need to multiply. Okay, there's something I can do in I don't know whether to use the trick or just to work it out with you. Okay, so what we could do is we could multiply both sides. Let's just go ahead and do this. This is not the way I would do it, but if you struggle a little bit with algebra, this might be better. So I realize on the left-hand side, I just get this multiplied by this, which is just going to be equal to 1. And on the right-hand side, I get P hat Q hat over N times, let's just write this as Z squared over the margin of error squared. Now I can multiply both sides by N. So I get N times, so I'm going to rewrite this a little bit as Z squared times P hat Q hat over the margin of error squared. So what this does, this gives us a formula that we can use to find sample size. Now, you're not going to have to replicate any of this stuff, so don't worry about that. You're just going to have to use the formula that we just created. All right, so let's see how that would work. So let's say that we have a 95%, so this is an example of the first case. We have a 95% confidence interval for P. And this confidence interval is, whatever, 13.2% to 47.6%. Now, using this formula, what do I need to be able to find? Well, I need my Z, I need my P hat, I need my Q hat, I need my margin of error. So my Z is obvious. From previous videos, we know that the Z critical for a 95% confidence interval is 1.96. I need my P hat, which is the value in the center of my interval. So I can do that by just, just by averaging those two values. I don't know if you're getting annoyed by it, but I sure am. 47.6 divided by 2, so the value of smack dab in the center will be 0.304, 30.4%. So I know my Q hat is 1 minus that. I can do this in my head, but I just don't want to take the chance. And I need my margin of error. Well, the margin of error is just the distance from the center to the edge, either one of them, or I could just take this number minus this number divided by 2. So I get my margin of error to be 17.2 or 0.172. All righty, let's plug and chug. So what do we know? We know that is what? Z squared times P hat times Q hat over margin of error squared. So if we can put all that in our calculator without doing something insane. And when I do that, I get 0.2748, or I'm sorry, 27.48. So I would need to round that up. So the sample size that I would need to create this interval would be 28.